Okay, we are recording. And now go to sharing the slides. Okay, let's get started. So, hello beautiful people. And to those in the A03 recitation, welcome to the A02 recitation. Today you've got me, Ferris, Jonathan, and Jack. Woo! Unfortunately, Michelle and Hazel are not able to join us for this evening, but yeah, you've got us three, and feel free to ask any questions that come up. So, let's get going. So starting off with the announcements. Number one, congratulations on finishing test 3 last weekend. Now you're gonna have to start working on your project 5, which is due in 2 weeks. So that's gonna be due next 2 Wednesdays. Project 4 demos are up and running, and they're scheduled to run the whole of next week. So make sure you've signed up to that. And lastly, homework 10 and the extra credit project, if you want to do it, are due next Wednesday. And again, the 3-day late policy still applies if you still have not used them. And one more thing, the TA applications are still up. Interviews are on a rolling basis. So if you are interested to become a TA for this course or other CS courses, make sure to send the application soon. So yeah. Okay, parallel systems. So recall that threads share the same address space and the page table of the process to which they belong. So say for example process 1, it has two threads, threads 1 and threads 2. Those two threads, they share the same code, the same global code, and the same heap space. What they do not share, however, is the stack. So thread number 1 will use stack number 1, and thread number 2 will use stack number 2. And this is important to remember because this is central uh, to figuring out how are we going to organize our threads, how how are we going to switch memory spaces between different threads, and what happens if we switch processes. So keep this in mind. All right, so there are multiple ways you can arrange threads. The first way is on a user level thread. So in this type of organization, your threads are going to be in your user space and not your kernel space. So but let me take my pen. Okay, I think the pen is working. So you have a kernel and you have a user space. Now the kernel does not see any threads. For the kernel, it only sees the traditional ready queue, which is a queue that contains all of the ready to run processes. So process 1, process 2, and process 3. But the threads are within each process. So process 1, it contains its threads, and these threads are organized by the threads library. So whenever another thread wants to be run, it has to go through the thread library, and the thread library will run the thread based on how the program wants it to be implemented. So a very important thing to note here is that hold on. Yeah, a very important thing to note here is that all of the threads in one process cannot execute concurrently, and this is one of the major disadvantages of a user-level thread. So this phenomenon is called the threads running in a coroutine mode. So whenever one thread runs, all of the other threads must block. So at any one point of time, within one single process, only one thread can run. And as you can imagine, this does not help a lot in a multi-threaded process environment. This is as if you're still in a single processor environment, and we are not taking the performance advantages that a multi-threaded system offers. So this is why we prefer not to use the user level thread system. And another disadvantage of using this type of organization is that, yeah, basically the same thing. The thread, um, the thread represents the entire process. So recall that within this organization, the kernel does not know that this system is thread enabled. According to the kernel, there are only distinct processes, and each of those processes, they run uniformly. They run within their own memory space. So there are no multi-threading that happens within each process. When I say multi-threading, I meant threads that do run concurrently and not running co-routinely. So this if the kernel sees that the smallest unit of execution is the process itself and not the threads that are contained in those processes, so whenever one thread blocks, that thread will send a call to the system telling it to block this thread. But the kernel does not know that the thing that it's calling for, that blocking call, is a thread. It only sees that the process is calling that blocking call. So what the kernel will do is that it will block the whole process. So whenever one thread wants to block, the entire process gets blocked. So this is another problem in a user level threading system. So there are a few fixes to this. Number one is the envelope OS call. So whenever a thread wants to make a blocking call, it has to go through the thread library, and the thread library will decide what to do, whether to thread switch or to block that blocking call, to defer that blocking call. And another fix we can apply is the up call method. So this involves warning that an incoming blocking call is going to happen, and this allows the thread library to decide what is the best solution of mitigation. What should I do in case that a thread wants to block the process? So going to the pros, because all of the threads only run within the same process. All of those threads, they share the same memory space. So whenever you want to switch, it is very easy and cheap to do because all of the threads, they share the same memory space. And in addition, the thread level scheduler is customizable for any specific process. So because all of the threads, they lie within each one single process, all of those processes, they can have different ways of implementing the thread organization. So yes, that is the user level thread. Any questions up to now? Oh no, I forgot to open the chat. Let me open the chat. Okay. Okay, I have a private question. Why does the OS break whole process in user level thread? So in this type of implementation, the kernel or the OS, that is not the entity that breaks the process. Instead, it is the process itself that breaks the process into multiple threads. So if the process knows that it will have a CPU burst and IO burst, it may decide to have two threads, one representing the CPU burst and the other representing the IO burst, and it can switch concurrently within those two threads in case that the second thread will need to be used. But in this case, the kernel or the OS is not itself aware that threads even do exist. It is only aware that there are multiple processes within the system. That's all. Okay, any other questions? All right. So the second implementation type of threads involves the use of the kernel. So instead of putting the threads within the user, we instead put it within the kernel. So as you might have guessed, each process can consist of several different threads, and the kernel can decide to change the threads whenever there is a need to. According to the textbook, whenever a specific thread blocks, or whenever a specific thread wants to stop itself, then the kernel can easily switch from that thread to the other thread. So this is again a major advantage in a kernel level thread because it allows for that simpler change. I'm sorry, let me reword that. It's not simple. It's more organized. It's more systematic because the kernel is aware that there are threads within the system, so it can modify those threads in a way that maximizes the efficiency of this system. So I have a quiz for you. Pros and cons of kernel-level threads. Which of the following are true on kernel-level threads? Mark true or false for each of the following 5 statements. Number 1, blocking calls are easy. Number 2, we cannot get through multiprocessing. Number 3, expensive thread switches. Number 4, the kernel becomes complicated with thread and process schedulers. And number 5, the thread packages are portable between OSs. So I'll give you guys 1 minute to write down true or false for each of the following statements. Okay, cool. We have quite an unanimous answer for the false being the second and the fifth choice. And that is indeed the correct answer. So let's go through them one by one. Number 1, blocking calls are easy. This is true because the kernel is aware that threads do exist, and whenever one thread is making a blocking call, then the kernel may easily switch between threads. Number 2, is it true that we can get through multiprocessing? Yes, we can get through multiprocessing because with the use of kernel level threads, there is no need for threads to be coroutine. Multiple threads can run concurrently, and this is where we get the true multiprocessing advantages. Number 3, expensive thread switch. Yes, it is expensive because every time we want to do a thread switch, we have to go all the way to the kernel and back to the threads to switch the threads, and that is not good. Number 4, the kernels become complicated. This is true because now you have two different types of schedulers. The thread scheduler and the process scheduler are all smacked into the OS, and so it becomes a bit complicated to write your software. And number 5, thread packages are portable between OSs. This is not true because the thread implementation is specific to each kernel, each OS. Each OS has its own way of implementing how the threads will function with different processes, and therefore if you attempt to bring those thread packages from one OS to another OS, that another OS may not be using the same thread implementation as that first OS. So yeah. Okay, so
Question about
go
how
on.
expensive kernel level threads are. Well, how expensive are they? Um, I mean, compared to user level threads, because you still have to do the same sorts of things. You have to relinquish control from one, set up the other, and have it execute. I mean, you don't really have to do a whole lot of swapping on the memory map. As long as you tell the OS they share a bunch of things, the OS just has to swap out the stack, and yeah, that's basically it. Surely, I mean, maybe the actually switching to kernel space would be expensive, but yeah, what's the expensive part?
Yeah, so recall in a user level thread, um, the multi-threads, the multiple threads, they only exist within a process space. So whenever we want to make a thread switch, it is only between two different threads of the same process. So recall back from what a thread shares, the only thing that we need to change in a user level thread is the stack space. That is all. But when it comes to kernel level threads, it is the kernel which has to decide what exactly has to change. And again, the threads here, they're not like confined to each different process. Instead, there are multiple threads of multiple processes and the kernel sees them all. So whenever thread 1 or process 1 wants to do a context switch, then it has to go all the way to the kernel, and the kernel must decide from all the way to the OS level what should be changed, whether that may be the heap or the code itself, the memory space. So there's a lot more changes that needs to be done in a kernel level thread compared to a user level thread, simply because of where we store those threads.
All right.
Okay. Hold on, I have a private question. So kernel level threads allow the system to manage the threads so that the user don't worry about it at a high level. You could say that that is true. I mean, there's still some things that you have to, be wary of whenever you want to code a thread switch. For example, where to put your mutexes. But yeah, most of the implementation, most of the hard work is now transferred from the process to the kernel. Now the process still has to put in the right code, but it's now the kernel which does most of the blunt work in managing the threads. So yeah. Any other questions? So the kernel level is now a thread manager. Yep, that is correct. Okay, now going on. Now we've learned about kernel level threads, and now we're going to learn about a specific type of kernel level thread, and this is what we call a Sun Solaris threads. So the difference in implementations that we add one different stage here, which is what we call the lightweight process. So a lightweight process, you could think of it as all of the currently active kernel threads. So the kernel has all of the threads it is available that it can use, and only some of those threads will be used to actually run the processes, to run the threads within each process. And the way how it is organized is that an LWP right now, an LWP is a representation of a process. So this is now the unit of scheduling, and LWP is itself a kernel thread, and that LWP, they represent every set of coroutine threads from the user process. So say for example, threads T1 and T2, they are coroutine, meaning one cannot run while the other runs. Only one of them can run at any single point. So it's easy to imagine that at any point, only one of those threads are in use. So you will only need one single kernel level thread to process, to run them both. And the opposite is true in that whenever we have two different not coroutine threads, then both of those threads will have to be run by their own distinct lightweight process. For example, T2 and T3, they are not coroutine, so they use two different lightweight processes. And going back to P2, sorry, going to P2, because these two threads, they do not share the same LWP, because they don't share the same LWP, so they are not coroutine. Both of them can run simultaneously, or both of them can stop, or one of them can run. So you can go anywhere it can. So which is why we need two different LWPs for T4 and T5. Yep. And you might
Question.
be one. Yep, Amar.
What exactly is an LWP? Why is it needed? I mean, it seems LWPs always map to kernel threads. So why not just say you can have multiple coroutines on a single kernel thread, and just go about it that way? Why do we need this LWP layer, I guess?
Jack and Jonathan, correct me if I'm wrong, but I believe that the LWP is not a physical entity. Instead, it is simply an abstract representation of the kernel thread. So
Well,
it is useful.
the same could be said for a kernel level thread. Each kernel thread has its own thread control block, and that essentially defines the state of the thread.
Hmm. I mean, yeah, that is true. I imagine the reason why we have an LWP is just to make the whole process easier, because it essentially groups all of the threads that cannot run at the same time into one single thread, and therefore it just makes the whole thread switching and thread management easier.
Mm.
And yeah, so you may have noticed some kernel level threads that are not in use, that are not themselves LWP. So those kernel threads are simply, available threads in case there are more processes that want to run. So we can use those processes. So yeah. Any
Can
other
you map
questions?
can you map multiple LWPs to the same kernel thread?
No, no, you cannot. So
Okay.
an LWP and kernel thread is one-to-one mapping.
Mm.
This cannot. So, 2-to-1 or many-to-one, this cannot happen. So
Mm.
it's always 1-to-one. Okay. Any other questions? 1, 2, 3. Okay, I have a quiz for you. Label the order of cost of these context switches, 1 being the lowest cost in terms of context switches, and 3 being the highest cost. So which one is it? 1, 2, 3, 1, 3, 2. I'll give you 20 seconds. Okay, everyone seems to be arriving at the same answer. So yeah, the answer is indeed 132. The cheapest in terms of context switch is between the same LWP, and the most expensive is between two different processes. So going back to our previous diagram, whenever we want to switch context between two different threads within the same LWP, remember it is only a matter of switching um, it is only a matter of switching the stack at the user level. But when it comes to switching threads between two different threads that are not sharing the same LWP, then you have to go all the way to the kernel to change the stack space between those two threads. And the most expensive option would be to have context switches between two different threads of two different processes, because now you have to change everything, the heap, the memory, the code, the TLB, everything has to be changed, not just the stack. Okay, so any questions? All right, now let's move on to test and set. So recall that threads share the same heap of memory space, and there may come a situation when two different threads of the same process, they may request the same heap memory simultaneously, and we need to make sure that this does not happen. Recall back in project 4 when you want to access the ready queue and you have to add certain logs, certain checks to make sure that those two different threads does not access the same memory heap. So this is what we're doing. We're trying to make sure that we're trying to implement that thread mutex lock to ensure that an unwanted race condition happens. So yeah. Now, how do mutexes work? Let's go into how exactly a mutex is implemented. So you can um, assume a lock as being an integer. An integer is stored at a specific memory location, and that integer may be 0 or 1. If the lock itself is if the lock is 0, then that means that lock is available to be used, and like other threads, other processes can ask for that lock to hold on to that lock. And now we want to make sure that the mutex itself is thread safe. In a way, we want to put a mutex lock on the mutex lock. So how do we do this? Well, this all goes back to the concept of atomicity. We want to make sure that no programs can interrupt a mutex while it is in progress. Yeah, while it is in working. Okay, hold on. I have a private question. When someone says a thread is blocking, does that mean a thread is stalling slash waiting? Yep. So whenever a thread is blocking, it is essentially waiting for something to happen, or it may just stop indefinitely. But it's just requesting that that specific line of execution is stopped. So yeah. Okay, so going back to mutexes. So whenever we want to make a mutex, we have two options, whether we want to lock or unlock. And if we want to unlock, we only have one instruction, so this is trivially already atomic. And this is guaranteed by the processor, by the CPU itself. Recall how you did implement the add instruction, the dollar instruction in projects 1 and 2. All of those instructions are atomic itself. So whenever we have any one single instruction that is atomic, that is not a problem. This is a problem. It's a big problem because you have a lot of stuff going on and you want to make sure that all of this is itself atomic. So how do you make sure that it's atomic? You introduce a new instruction. So aside from add, addy, dollar, save word, load word, you add one more instruction which we call the test and set instruction, or TAS for short. And this instruction, by definition, is atomic. So whenever it's running, no other threads can preempt or interrupt this instruction. So how it works is that it takes in a memory address, which points to an integer. Remember the lock that we talked about, the lock being an integer which is residing at a certain memory address. Well, here is where we use it. A test and set instruction takes in the memory address of that lock and it returns the current value of that integer. And whatever happens, it sets the integer to 1. Okay, so yep,
Here's, I have a
yep.
question. So for the test and set, I'm a bit confused on like how this is actually solving the problem. Like, especially with the part where you're setting the memory like thing to 1. How is that like solving the exact problem? How is that solving the problem we had before? Like, besides the fact that you're putting it all in one instruction, like I don't see how setting the memory location to 1 like simulates the lock. Could you like explain that a little bit?
Mhm. Yep, so memory lock, it's just a very simple representation on whether a certain lock is available or not. So it can be 0, that means the lock is available, or it can be 1, meaning that it is held by another thread. So what we want to make sure here is that when we want to change that that value in the lock, we want to make sure that as we are changing, nothing else, no other threads is simultaneously changing the lock, because you can imagine that if thread 1 wants to hold a lock, but as it is trying to get the lock, another thread also wants to get that lock, and a data race happens and bad stuff happens. So we don't want that. Now, in order to make sure that that does not happen, we want to make sure that our lock mechanism is atomic. We want to make sure no other threads can do the same instruction at the same time. So say for example, T1 is here. It has already gone through checking whether memory lock is equal to 0, and it seems that the lock is available, so it attempts to lock that lock. But then another thread T2 comes into the picture and it swoops down that lock. And now T2 holds that lock, but T1 also thinks that it holds the lock, and that would be a disaster because no two threads can hold the same lock. Does that answer your question, Karthik?
You're just trying to use with the test and set instruction, ensure one thread can access that shared resource, maybe address set 1000, for example, right?
Mhm.
You're just trying to ensure that, basically, with test and set.
Yeah, so I think it's best that we try to look at this example, how it is used. So, okay, so we don't have this old instruction anymore. We now have the test and set instruction, which returns either 0 or 1. So say thread 1 wants to lock using a given lock at a certain memory address. It doesn't matter. So first we check whether that lock is available or not using the test and set instruction. So say that lock is available. The lock value is 0, so it is available. So this while condition goes false, and within that test and set instruction, that lock value is already set to 1. So we return success. So yeah, that is a success. But what if the lock is unavailable? The lock value is 1. In that case, the test and set instruction will return the current value of the lock, which is 1, and 1 denotes failure. So in that case, it will go into this while loop and block the thread as long as test and set returns the value 1, meaning the lock is not available for this thread. And at the instant when the lock is now available, when test and set deems that L is available, then this all goes false and we return success. Does that help, Karthik?
Yeah, I think that kind of helps. So what that means is for the loop to get out, that means
Mhm.
the thread that's holding onto the lock has to explicitly say, I want to unlock it, or I want to give it up, right?
Yep.
Okay.
Cool. All right. Now, multiprocessors. Now, a multiprocessor, as its name suggests, is a system with multiple processors sharing the same memory. So you can have, for example, 5 different processes sharing the same memory, and all of these processes will have to coordinate with each other to make sure that they don't manipulate. There isn't any unwanted race conditions that happen when they're accessing the shared memory. So we covered that part. How does a multi-threaded process make sure to synchronize the access of the shared memory? We use mutexes. But now we have run into one other problem, and that problem is cache coherence. So these are the 3 things that as an SMP, a symmetric multiprocessor, must ensure in order to have a fully functional multiprocessor. So besides solving the problem of cache coherence, we also have to make sure that number one, the threads all of the threads of the same process share the same page table, this can be easily achieved with a function called a TLB shootdown. So meaning whenever we want to evict a page, we evict any and all TLB entries for that page in any threads. Number two, it has to guarantee atomicity, and this is solved by test and set, which we have discussed a few minutes ago. And the third one we have to protect from is the problem of cache coherence. So recall that a processor can have its own cache. So remember that cache is where you store temporary copies of memory to reduce the amount of time that you need to have to access a certain variable, a certain attribute in memory. Use caches. But now when you are talking about multi-threaded processes, then you have the problem of multiple processors holding different values for the same memory location in their caches. Remember, mutexes do not solve this problem. So how do we solve this problem? There are two ways we can solve this problem. So number one is write invalidate. So whenever a certain memory location X is modified, then that CPU will send an invalidate signal to all of the other CPUs saying, hey, y'all, please cancel, please invalidate this memory location if you have it in your pure cache. So say, for example, CPU 1, it's changing the value in X to another value. It writes to X. So what it will do is that it will send an invalidate signal to all of the other CPUs, telling them to change, to invalidate the entry for X in their own caches. And the second solution is write update. So this is simply sending an update command to all of the CPUs. So if CPU 1 changes X, then it will send a call to other CPUs telling them to get the new value from the shared memory. And yep, that is all for cache coherence and multiprocessors. Any questions? Okay, I have a question. I think I see how this is different from just having one common cache. If all have to have the most updated value. So there is a slight advantage in several in the processors each having their own cache, um, each having their own caches. So let me think. So think of, for example, the first CPU. It For some reason it only works with process 1, and the second CPU it only works with process 2. So in that specific case, both of them can have completely different caches with completely different memory values, and yet they're still synchronized with each other simply because they're using two different processes. This is in contrast to them having a single cache which they have to share between each other. So if they have the same cache, then if one CPU wants to change something in the cache, then the other CPU has to wait. And this does not happen if each CPU has its own cache. So there is that subtle advantage for each CPU having their own cache. But yeah, you are correct in that if they are trying to access the same memory space, then it might as well make more sense to have one single shared cache. So yeah, any other questions?
Yeah, I got a question.
Go on, Karthik.
Wait, so for write invalidate, right? So if
Yep.
let's say CP1 wants to modify location 5000, right?
Mm-hmm.
And put a new number in there, right? So then for the invalidate bit, you'll send an invalidate signal. So then will CPUs 2, 3, 4 all the way to N also update their entries? And if so, where's that update going to come from? In the write invalidate like methodology.
Okay, yeah. So in the write invalidate methodology, the other CPUs they don't update their memory location X. So recall a cache, it has a memory value, memory address, and a valid bit. Okay, so when a single CPU receives a signal that a memory address 5000 is now invalid, so all it does is it changes this valid bit to invalid, and that is all that happens. If in the future CPU 2 wants to use the value inside memory address 5000 and it sees that the valid bit is invalid, then it has to go all the way to shared memory and update its cache.
So that means all these methods rely on the assumption that the shared memory is always the most up to date, like the most latest, right?
Yep,
Like it's always.
exactly.
Oh, okay. I just wanted to make sure.
Cool.
But thank you.
Cool. Any other questions?
Oh, Ferris, I have a private question actually.
Okay.
So someone was wondering, how is the test and set instruction different than the condition wait and condition signal that we use in the project?
Let me think. Wait and signal. Yeah, that's a quite good question. There's a lot of similarities between even how the code is implemented between a wait and signal, but I would guess in that in the test and set instruction, going back all the way. So one difference is that in the test and set instruction, it always checks whether it keeps on checking whether the lock is available or not. So this is different from a wait and signal. In the wait, you just stop doing everything. You stop doing everything. But in the test and set instruction, you keep on checking whether that lock is available or not. And at the instant it is available, then goes into the while loop. Goes out of the while loop. Does that help, anonymous student? Okay. Okay. All right. So if there's nothing else, Jonathan, you're up.
Oh yeah. Okay, so I'm gonna share. Am I gonna share my screen? Yes, I'm gonna
Yep.
share my. Okay.
I'll stop sharing.
Cool. And current slide. Okay, cool. Wait, y'all can see my screen, right? Okay.
Yep.
Cool. So, wow, we finally made it to the second part of the name of this course. So, intro to computer systems and networking. So we're moving to the networking portion. So I guess a little bit of an intro to networking. Some definitions or terms that we need first are the host. So a host is just a computer that's connected to a network. So whether that's your phone or any device that connects to a network. And now, so what is a network? So a network is a group of computers that are linked together to share resources. And then together, that can make an internet. So that's several smaller networks together on using an agreed upon protocol to communicate. So then we kind of use this protocol stack to interact with the network, and that's kind of how we pass information along between different hosts in the network. So what's our protocol? This is our protocol. It's the IP stacks and the internet protocol stack. And so there's 5 layers to it: the application, transport, network, link, and physical layer. So the application layer is what sends application-specific messages. The transport layer sends segments. The network sends packets. The data link sends frames, and then the physical layer sends individual bits. And so they kind of interact with each other, and we'll kind of go over through some of these. I think we're talking about transport, network, and the link layer today. Or transport, link, and physical layer today, and then we'll be covering the network layer next recitation. So we have the transport layer. so it packetizes data from the application layer into packets to be transported. So from the application layer, the application layer is kind of anything that like an application-wide like communication. So kind of like an internet like request. That's so when you access like a website, that is an application layer, something on the application layer, or instant messaging. That's something that's also on the like application layer. So when we want to communicate between that, we have to packetize the data to send them back and forth between the devices. So how do we send these packets or like segments? So we have the stop and wait protocol, which is one way. So the sender, we have, if you look at the diagram over here, basically the sender will send a packet and then it waits until the protocol, the receiver has received the packet. And then when the receiver will send an acknowledge signal, an ACK signal to the sender, letting it know that it received the packet. So if there's a timeout, or if something is wrong with the packet, like the packet's been corrupted or didn't receive it properly, it won't send that ACK signal. And then after a timeout, the sender will know to resend it. And so we do need to know that we need to have a way to check to make sure that it's not just when we receive an ACK signal, we're not getting like an old packet that was, or when we're sending a packet, we're not getting an old packet that just happened to be delayed. So then we have this alternating zeros and ones bit in the protocol that lets us know which packet it is. And the thing about stop and wait protocol is that it's really, really slow because basically we're just waiting. Most of the time is actually just spent waiting for the ACK signal. So we have a way to improve upon that, which is pipeline transmission. So pipeline transmission sends like sets of packets before we get the acknowledge signal. So in the stop and wait protocol, we would only send the next packet after it's been confirmed that the receiver has received the packet by sending an ACK signal. So in the pipeline transmission, we send groups of packets, and we don't necessarily need to acknowledge every packet, and that just depends on what protocol we're using and the case that we're using it in. So we have something called the reliable pipeline transmission, and that's the receiver does acknowledge each packet, but then we wait for the acknowledge signal, and then when we get that ACK signal, we move the window over. So this is kind of what it looks like. We have so the green right here, these packets have been sent and acknowledged, and then we have our window right here. This is window size of 10, and then we have the next 10 packets, which are shown right here in the red and the blue. So the red are the packets that have been sent but not yet acknowledged, and then the blue are the ones that we can send without waiting for any. We can send without waiting for acknowledged signals. So then if we have that same diagram from the previous stop and acknowledge, it kind of looks like this, where we can send packets in sets. So in this one, we have a window size of 4, and then so when packet 0 has been acknowledged, then we can send packet 4, and so that's kind of what this looks like on the like in a diagram way. Does anyone have any questions maybe about like stop and acknowledge and the pipeline transmission?
Yeah, I have a question.
Yes.
So could you clarify like the part where you say like well, first off, what's the advantage of like just doing ACK on every packet versus sending one ACK for one set of packets sent? Because you said like that the acknowledge, like, do we need to acknowledge every packet depends on like the protocol or like the the way you're handling it, right?
Yeah.
So
So
could you clarify the advantage?
the ACK signal is just a way for the receiver to confirm that to confirm that it's received the packet. And so sometimes we don't need to acknowledge every packet. And there's actually protocols that don't acknowledge packets, and we just kind of deal with the data loss, or like the packet loss. I think we can kind of, there's one, I think UDP is something I'll cover a little in like a couple slides, and that one you don't need to acknowledge. It's just you send this information, and then hopefully it receives it, but there is no like acknowledge that that we received it. So sometimes we can lose bits. Sometimes we can lose information, and sometimes it just depends on the situation whether we're okay with losing information or we're not okay with losing that information.
Okay.
What if like packet 1 is lost, and then so the ACK1 is not received by the sender, but like package 2 is received, so ACK2 is received by the sender.
Yeah, so that's actually a little bit more complicated of a situation. So basically, each packet has a timeout. So we'll wait. It'll go ahead and send packet. It'll go ahead and send the next packet, but then we'll wait until packet. You said packet 1 doesn't send, right? So packet 1 will actually wait until it times out, and then it'll have to try to send again in the next grouping. And that's a little bit more complicated of a thing. And I think, yeah, so it's a little bit more complicated of a topic. I don't know if have we covered this in class. I don't think we've covered this in class. But basically, you have to. There's a timeout. The packet has a timeout, and then if it doesn't receive the ACK signal for that packet, it'll have to resend it after with a different group of packets.
Okay, yeah, that makes sense. So do we have to like kind of know this?
I don't think we covered it. We don't cover it this deeply in this class, right? Jackson, Ferris?
Yeah.
No, there's no timeouts in this class.
That's
Yeah.
networking.
Yeah, networking. It's a really interesting class. So if you're really interested in like any of this networking stuff, that class is basically just all of this. And you go into like all of the details about how like things are sent, what happens if we lose a packet, like checking to make sure we get the values properly. So that's and that's, now that you've taken this class, you can take networking too. But yeah, so that's kind of how it works. It's a little bit more complicated of a, and I think it's a little bit outside the scope of this course.
Okay, thanks.
Okay, cool. Are there any more questions?
Yeah, I have a question.
Okay.
So what if there's a scenario where like I try to send like, let's say packet 0 and I get a timeout, so I send it again, and then I send it again and again and again. Is there like an extra like timeout counter on number of attempts to send a packet?
I don't think so. Is there? I took 3251 a while ago, and I don't remember.
Am I correct in saying that that would have to be regulated by the application layer? Because, like, for instance, ping will just keep trying to send packets, and it'll loop infinitely until you kill it. Although I don't know if that's just. I mean.
That is a very good question. I think it's a little bit outside the scope of this course, but if you're interested, I'll try to look it up for you, because I actually don't remember from my networking class. There's something quite specific. It's like checking for. It's like there's a lot of. I don't entirely remember, but if you are interested, I will try to reach out to you and take a look at that.
Okay.
Okay, cool. So we can talk about so going into like going kind of back to pipeline protocols. There's two types of pipeline protocols. We have TCP and UDP. And so TCP is transmission control protocol. I think it's transmission control protocol. And it's connection oriented. So that basically means that when we do a TCP, when we send packets with the TCP protocol, the sender and the receiver have an explicit it'll send explicit signals to establish a connection to make sure that the receiver is able to receive this information and that they're communicating with the same protocol. So in addition to that, so there's a thing about I don't know if we're going to cover it. We briefly mentioned in the book, it's a TCP three-way handshake that basically establishes this connection. And then only after we establish that connection can we start sending packets. And then TCP is also self-regulating. So it's able to monitor the flow. And if it's starting to become too it can monitor like the rate, and if it's becoming a little bit too slow or it's not, the packets are not, it can modify the window size and the number of packets it sends at once to like optimize like the transmission rate. And so TCP also sends acknowledges, and so it when it receives a packet, it needs to acknowledge that it's received the packet and then the packet information is correct. And then TCP also uses windowing, that the window pipeline that we talked about before. And so the pro of TCP is that it's very reliable because we always acknowledge when packets arrive, and then if we don't get that acknowledged signal, we'll try to resend the packet. We can always make sure that it's very reliable, so we can make sure that we're getting the information that we need. So one of the cons, though, is that connection setup and teardown is it takes, you need to establish that setup and that connection. And then there's also no guarantees on the delay or transmission rate because we need to make sure that we're receiving all of these packets. And so TCP is used quite often in the internet. So web browsing, messaging, email, and those are things like, so for example, in email, we want to make sure that when we send an email, we get all of the text at once. We don't want any missing packets so you'll have like an email and then maybe a couple of missing areas. So that's TCP, and that's generally, it's considered more reliable. And it is more reliable, but it's just a little bit slower. And so the other one that we have is UDP, and this one is it's very simple actually. So it's connectionless. So when two computers are trying to send information, the sender doesn't establish a connection. It just kind of just sends the information without really making sure that the receiver is ready to accept that information. It's also unregulated, so it can't really control the rate that we send packets. In addition to that, we don't acknowledge that we've received the packet. So kind of going back to like whether or not we acknowledge, this is using UDP, we just don't acknowledge. So we sometimes we lose packets, and that's just kind of assumed to be okay in that case. And we don't use windowing in this case either. And so some of the pros of UDP is that it's very simple and it's very fast. So we use it in environments that like by their nature have low packet loss, or that have a tolerance for packet loss. So like if we lose some information, it's okay. But the cons to that is that it's not reliable. So we can't guarantee that we're receiving information. And we also can't, the messages can be received in any order. And in addition to that, it's not regulated, so there can be network congestion sometimes. And there's also no guarantee on delay or transmission rate. And so UDP is usually used in like applications where we want speed or latency is really important. So for example, we're all like video calling right now. Video calling it's okay to have maybe a couple packet loss in the name of speed. Like we want to have some real-time conversation, like a real-time communication, not waiting to make sure every single thing is said. So in the name of latency, sometimes we lose packets, and sometimes that information is just not there. So that's why sometimes like we can cut out and we don't hear things, and that's sometimes just packets are just lost and we just never get those. Yeah. So does anyone have any questions about TCP or UDP, the two pipelines protocols?
Would it be correct to say that in terms of the transport layer, UDP is sort of the, I guess, quote unquote, identity protocol, in the sense that it doesn't add anything to the network layer, it just sort of forwards it as is?
I think that could be an analogy. It's definitely simpler than the TCP. I don't know if it's correct to say it doesn't add anything to the network layer.
I mean, do you need in addition to your Ethernet header, IP header, do you need a UDP header?
I believe there is a UDP header, and there's a way that there is a UDP header actually. I'm pretty sure Jackson or Ferris.
Yeah,
We can 50-50.
Jackson confirms.
There is a UDP
Yeah.
header, so it
It's
does
limited,
add,
but there is.
yeah. So there is information that we add to UDP, but it's definitely simpler than TCP, and there's less information that the UDP header has.
Hmm.
Okay, cool. Are there any other questions?
Yeah, quick question for you, Jonathan. What is a UDP header?
So a UDP header is just that's starting to go a little bit outside the scope of the course, but basically when we send a packet, we have a little bit of information that we put at the beginning that's kind of like where it's coming from. What else is in the UDP header? Oh, I don't remember, but like
Where
it's
it's
just a little bit.
going?
Yeah,
Where it's
I
coming from,
have
where it's
the
going.
I have the Wikipedia article up right now. It's just port, source port, destination port, length, and checksum. Checksum is optional in
Yeah,
IPv4.
yeah. So it's just a little bit of extra information. It's like where it's coming from, where it's going, some stuff like that. That's kind of useful, but yeah. So that's what. And then the TCP also has a header as well, and that has a little bit more information, but it also kind of contains where it's coming from, where it's going. There's a check. Both of them have a checksum, which is a way to make sure that the information, the packet information, is like non-corrupted. But yeah, that's just kind of what the header is, and yeah. Does that kind of answer your question? It's a little bit starting to go a little bit outside this course.
Answers the question.
Okay, cool. Are there any other questions? Okay, cool. I think, yes, so that brings us to the link layer. So I will stop sharing my screen and hand it over to Jackson.
All right, perfect. So yeah, we're gonna basically just skip over all of networking. We don't have to really worry about, how packets get from each other. We're just gonna care about how we actually transmit it on a wire. So that's what the link layer is. But before I get started, can everybody see my screen? Can everybody hear me okay? Just a quick
Yep,
mental
okay.
check. Awesome, perfect. All right, so talking about the link layer, we've already talked about essentially, okay, we've got the application, we know what data we want to send. The transport layer says, all right, what exactly, when we get to that destination host, that destination machine, how do we actually handle that packet? We're jumping over networking, which is basically how we get from one host to another. And instead, we're going to be talking about, okay, how do we get from one router to another router? Like, how do we actually physically connect our two hosts? And it's a little bit backwards. We haven't gone over it in lecture. So if you have any questions about the network layer, let us know. We could probably answer it, but we will cover it next recitation for sure. So link layer. Link layer basically manages the physical layer. And you'll notice that a lot of the protocol stack, it manages the one bottom, or it gently presents something nicely for the next one. So the transport layer gently presents, oh, here's what I have, here's my payload, here's where it should be going, here's where you should be bringing it to. So for the link layer, we want to manage the physical level. We want to say, all right, how do we actually access the physical level? How do we actually access the wire? So big part of the link layer is how do we actually link two things together? So we need to acquire the physical medium, whether that's a wire or whether it's wireless. Also, we need to understand, well, we have data from the network layer, so how do we actually send that data to physical wires? Like, how do we send it on the wire? So we'll talk about MAC addresses, we'll talk about how we actually physically grab it, and we'll talk about actually sending the frames of data with Ethernet and token ring. So Ethernet, fairly simple. Most of y'all should understand what Ethernet is. It's the thing plugged into my computer right now. And we can kind of think about it as this big, big wire that connects a bunch of different computers. and they're all identified by this NIC. This NIC is the network interface card, and this is basically your address, like how you identify yourself on a physical wire. Now, on this cable, we have a bunch of people. We have a bunch of people on, we have a bunch of NICs. So how do we actually know who is on our wire? Well, this is our broadcast domain. All the people on our wire is the broadcast domain, and everybody has their own unique MAC address. Now, having a shared bus, I want to like draw a big parallel to, oh, the processor, LC2200. We had a shared bus there, and we had like little drivers. We had, oh shoot, what were they? It was tri-state buffers in order to make sure there weren't any collisions there. But for Ethernet, we don't have that. So when one or more of these computers, when one or more of these hosts basically say, hey, I want to send data, how do we actually say, okay, well, I'm sending data, so you back off, or I'm sending data, you back off? How do we actually say who gets to go? So for Ethernet, we use this big fancy little acronym. It's Carrier Sense Multiple Access / Collision Detection. You don't need to know the full acronym, although you should probably be able to recognize it on a test. But the whole idea for this is we're not trying to completely avoid collisions. Collisions are going to happen because we have a shared wire. Instead, what we're going to say is, okay, collisions are going to happen. When collisions happen, we should back off. Like somebody else is trying to communicate, somebody else can go from there. So the whole idea is that when I'll go through this little state diagram, but let's say we want to transmit something. So boom, we're going to listen for the wire. We're going to listen on the wire and wait for idle activity. Idle activity is basically, well, since it's a wire, is it fluctuating? Is it going up and down? Is it staying all high? Is it staying all low? Is there any activity? If there's not any activity, well, great. Then we can start transmitting our frames. We can start transmitting our zeros and ones onto the wire. Now, what happens if we transmit onto the wire, but we look at our data, like we know that we're sending a, a byte, basically. We're saying 0011, blah, 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 a bunch of other numbers. What happens if what we're trying to send, looks different than what is actually on the wire? Well, in that case, somebody else probably trying to send more data. So little ones and zeros are all combining onto the wire. So now we're kind of screwed. We've detected a collision. Basically, the value we sent is not the value observed. So if we observe a collision, we want to say, all right, hey, back off. We're going to send noise. Oh, shoot. I just ripped my headphones out. So basically, when we get an apology, when we get a collision, we want to send an apology. We want to basically say, hey, everybody, there was a collision, so back off, and then we wait for a random amount of time. Now, this exponential back off that you see up here is basically the idea of that as more people are trying to send stuff onto the frame, we want to back off more. We want to back off exponentially. So the more collisions we have, the more time we back off before we resend frames. Okay, with this collision detection, we're basically saying we're going to send as much as we can. We're going to not worry about actually avoiding collisions, but when we detect, we'll back off and wait and retry later. How do we feel about this so far? Yay or nay? Any questions?
Yeah, Jackson, I got a question.
Yeah.
So for frame versus packet, is frame like kind of like the when you're saying about the ones and zeros and all that?
So yeah. Basically, every single layer in this transport has its own like encapsulation of data. So the application just sends, hey, I want to send an email. I want to send this. The transport layer says, well, we can't actually send this much data, so we'll packetize it. But network layer says, well, where is it actually going? So we need to add more fluff. We need to add a header to that. And then the link layer says, well, this big network thing is too big. I don't know how I'm going to send it, but I know where it needs to go. So I'll frame it. I'll basically pick and choose. I'll separate it. I'll chop it up, and I'll essentially send those little frames to wherever it's going. Because the network will say, all right, use this wire and send these frames. So the frame is basically encapsulating the data of the network layer, of the transport layer, of the application layer. And it just goes up like that.
So it's kind of like you're chopping up those packets way further into tinier pieces, I guess, seeming like in
Exactly.
the link layer.
Exactly. And it really depends on like the wire length. Like if we have, a 10 megabit wire, which would be very, very short, versus a gigabit wire, like we could send much, much, much bigger frames or many, many frames down the wire at a time. Does that make sense? Like our physical capabilities limit our frames, which limit network, which limit transport, etc.
Okay, I think I see the layer of abstraction. Thanks for clarifying that.
Yeah, of course. All right. Any other questions about collision detection?
Yeah, how exactly do we do collision detection?
Yeah.
Because we can't just assert 100 onto the bus at the same time. We'll run into a short.
Hmm. Well, essentially, if a bunch of people are trying to transmit on the wire at the same time, we're getting into physical stuff, which kind of goes over my head. I'm not an EE, unfortunately. My roommate is. I'll bug him later. But essentially, when we send something onto the wire and it's not what we receive, like it doesn't match up, then we know somewhere somehow we had two things transmitting at the same time, right? Like if we go to like the processor, like the LC2200, and we try to transmit two things onto the bus at the same time, well, yeah, we'll get a short or a collision in that case, but the value on the bus won't be the same thing. Like there'll still be an electrical value there that we can observe and we can look at, but it'll be wrong.
Okay, I mean, what I'm sort of okay, that gets more into physical, I guess.
Hmm. So I wouldn't worry too much about the physical. Just know that in terms of the link layer, we send frames of data, and whether or not we receive those same frames back on the wire, whether we observe those frames, if it's unchanged, there's no collision. If it is changed, there is a collision. And that's basically the only abstraction we need to know for this class.
All right.
Yeah. I'm sorry, I don't know too much about physical stuff. We can look it up later if you'd like. But moving on in terms of other different types of collision, well, what happens with Wi-Fi? What if we don't have a shared medium? Well, in this case, we can't actively look and see at the exact same time. We don't have a shared wire. Instead, we're just sending stuff out and we're receiving a bunch of stuff. So in this case, we can't really detect as easily. It's not as feasible with a physical wire as it is with wireless. So in this case, we say, all right, well, screw the whole detection. We're just going to avoid it entirely. We want to take extra steps with wireless in order to avoid collisions entirely because we get this little hidden terminal problem where essentially we have a big you can imagine a big hallway where Joe is talking to Cindy, Bala is talking to Cindy, and Cindy is talking to both Joe and Bala. But if Cindy can only handle one frame at a time, if Bala and Joe are both talking and both screaming at them, it's very hard to hear any certain thing. So in this case, we have this little handshake called RTS CTS, or request to send, clear to send. So somebody that wants to send a packet will say, hey, I want to send something wirelessly to you. It cannot send until it gets the clear to send back. Now remember, everybody in a wireless environment, even if they're far away, can probably hear this packet. It's all globally. So unless you get your CTS back, you don't send, essentially. So we're completely avoiding that by having kind of like the TCP handshake where we don't send before we have a connection. We're not going to send things over the link layer. We're not going to send things over wireless until we get our clear to send packet. Basically, yeah, it's like ready, set, go. And these packets are so small anyways, so that if there are multiple collisions, like if Bala and Joe both send an RTS and it collides with Cindy, it's less damage. There'll still be a collision, and Cindy might have to handle that. I really don't know. The book doesn't go into too much depth about that. But what it does say is that they're so small, we don't really care. So we keep on sending a request to send until we completely avoid a collision, and then we get the clear to send. So difference between detection and avoidance. Avoidance, we wait for like a handshake. Detection, we just say, screw it, let's send packets. If it doesn't turn out right, well, we'll back off. How is the difference between avoidance and detection? We feeling good? Feeling good so far. Good, good, good. Hope this speaks for the rest of the class, but hey, Let me know if not. Interrupt me, please do. So we talked about this. We talked about the Ethernet. And Ethernet, it's random access. We randomly access whenever we want. We access the physical layer whenever we want, basically. We want to send a packet, boom, send it. Token ring is a different approach to this, and it's basically, all right, I don't want to randomly access. I don't want to take over the physical layer whenever I want. Rather, it's turn-based. So kind of like a turn-based video game, everybody has their own turn, and everybody's turn is marked by this token. So a token, just a special bit value that's predetermined on the wire that says, hey, when you look at this and when you get this on the like little wire, you can send something if you want. If you want, of course. If you don't, then you'll clearly send the token away. But it's basically like a hall pass. If you want to send something, or if you want to go in the hallway or send a note to another class, you basically have to have this hall pass before you can go. You have to have the token before you can put something onto the wire. Now, this is great. We have zero collisions now because nobody will send without the hall pass. Nobody will send without the token. But it's also slow. Let's say we have a bunch of people that are trying to, work. Well, it's great because then we can say, all right, if you're trying to send a bunch of packets, well, great, there won't be any collisions and it'll get there safely. What if there's only a limited amount and I'm not trying to send too many packets out? Well, if I'm waiting all the way around for the wire for the token, I might have to wait a really, really long time. Like the latency in order to send packets can be a lot. Does that make sense? So let me look. Okay, does every computer have one token? And if so, is the token circulating? Which computer has a turn? I think it's one token per wire, and the token is constantly put on. So basically, the token is constantly put on to the wire after the frame. So essentially how it's working is that we package the frame and the token at the same time so that we wait for the token. Like let's say the source wants to send to destination. Well, source is going to receive the token. It's going to look on the wire and say, oh, shoot, it's my turn. I get the token. Great. Perfect. So we'll package up the frame. We'll send that down the wire. And then when we're done sending the frame, well, we'll wait a little bit and then we'll send the token back. Because ideally we want everything to pass around because either the destination is going to have to remove the token and send it on its way, or the source is going to have to wait until the token gets all the way back to it. Whoever needed that like data, whether it was going to all the nodes on the wire or just a single node, well, it gets back to the source. And so then after the destination, however many destinations receive the package, gets the frame out, the moment the frame comes back to the source, we know, oh, hey, anybody that needed our frame of data got it. So now we'll wait for the token, and instead of, keeping the token, we'll just pass it off. It's the next guy's turn. It's next guy's turn for the hall pass, next guy's turn to send data.
Yeah, I have a small question though with that.
Yeah.
So basically, if I'm trying to send, so I get the frame and all that, put it on the token, and like the token is kind of like the delivery guy, right? So he's gonna like deliver it. But when the computer, like let's say there's an intermediary computer that sees that a token's coming on, will it like kind of do some validation and see like, oh, is the frame intended for me, kind of? And if not, like,
Yeah.
oh, just pop the token on.
Yeah, exactly. So the frame is going to travel along the wire, and whenever we get to a new host, whenever we get to like a new node, we'll say, "Oh shoot, was this like is the MAC address like for this like physical frame?" Because remember, all of our like computers are addressed in the NIC. Everybody has their own unique address here at this level too. Well, is it for me? Is the MAC address mine, or is it a broadcast? Is it for everyone? And regardless, it's going to pass that frame along until we get to the source. There's also another issue if we have a very, very big, like lots of distance between nodes, in which case the destination might remove the frame and pass on the token from there. That's a little subset thing. But the whole idea about token ring is that the token and the frame pass through the entire ring, and only when you get the token can you send something.
Wait, but then one more thing is, so like I understand the NIC is the identifier, and the like each computer, like as the token circulates, it's gonna see like, oh, there's a frame, and if so, is it for me by comparing the NIC, right? But
Yeah, the MAC
if the
address.
token,
Yeah.
right, so if the token comes back around to the sender, is that like the implicit acknowledge? So there's no external acknowledge. It's like implicitly, okay, somebody received it, so that's good.
Well, remember that there can't be any collisions. So the moment that the frame comes back to the sender, we know that whoever needed that frame has the frame. Like we're not worried about data collisions. So sending that frame out, we know that it got to its destination. So then we know, all right, well, I'm done with this, so we can move on, basically.
Cool. Makes sense.
Yeah,
Question
good question.
about token ring in general.
Mm.
Is the ring, I guess, a shared bus, or is it only like computer 0 can talk to computer 1, computer 1 to computer 2, and so on?
If I'm not mistaken, I think it's the exact same thing as like an Ethernet cable. It's like the same wire. Like they both have a shared bus. I'm pretty sure that's right. Ferris, Jonathan, can you correct me?
Because if it is, then couldn't you run into issues with collisions? Like, suppose you send the token, but then nothing happens on the bus and you don't know if the computer actually received the token. So you go to retransmit, and at the very same time, the computer that received the token is sending the acknowledgement for that token.
Well, there's not any acknowledgements for tokens.
Well, then what if a token gets lost in transmission? What do you do then?
Well, ideally we don't like so at the physical layer, ideally we never lose the electrical signal like between one host to another because ideally we have repeaters there. And like the repeaters will say, okay, oh, token, you're getting a little bit weak on your electrical signals. Let me just repeat what you just said. Um, so ideally we never run into like electrical issues like that. And if we do, that's another issue. And probably not our problem. Probably
Although
the
the
network people.
The link layer doesn't provide for reliable transmission, does it?
No, it doesn't. So in that case, if we get down to the link layer and we lose the packet, it would be the TCP, if we're using TCP, the transport layer's responsibility to say, hey, we never got the acknowledgement. It never routed through perfectly. We lost a packet, we lost a frame, etc.
But
So
the token ring operates on the link layer, so it can't be
yes,
guaranteed that. Okay.
I think. Wait. You're saying it can't be guaranteed.
It can't be guaranteed that the token will make it to its other.
I'm pretty sure that in lecture he went over this and he said that networks have like a manager, and if they don't hear the token on the ring after a certain timeout, then they'll put it back on the ring.
Yeah, I remember
Good
that
point.
too, but what if multiple computers try to do that at the same time?
There should only be a one manager, right? I mean, I wasn't at lecture, so I unfortunately.
Yeah,
Yeah.
I think he meant it would just be one manager. Yeah.
Somebody that manages the token and makes sure it's continually propagates through the line.
Hmm. All right.
Okay, cool. Good question. All right. So we talked about token rings, we talked about Ethernets. Little quick recap. Talking about the cons, I didn't really talk about the cons too much, but in terms of Ethernet versus token ring, the cons of Ethernet, because we're just doing collision detection, if we have a bunch of people trying to transmit on the wire, we get too many collisions under like that high load. That's what I was talking about, like the high load of trying to send something on the wire. And that causes a bunch of latency issues where we'll just have to back off a lot before we can actually send it. Whereas the token ring handles like people trying to send a lot of things on the wire perfectly because we send as many frames, we'll send our frame when we get our token perfect. But in terms of con, if we're not trying to send a bunch of data on the wire, well, there's an issue because at that point, the latency to transfer the token all the way around the ring just becomes really slow. So take a look at this link layer. You'll have to know a little bit about this. I didn't want to go too in depth because we probably won't test you. We'll test you on like the different types of collision detection and avoidance. We'll test you on whether you know what Ethernet and token ring are. But in terms of like more specific physical things, we're really only going to cover Manchester encoding and how we actually send things on the wire and how we say, okay, well, how do we know when we're sending things on the wire versus not sending things on the wire? Like, obviously, we can say, oh, logical 0, we'll just have it be a 0, or logical 1 will just be a 1. But how do we know we're not just sending 0, 0, 0, 0, 0, 0, and the line is idle? So Manchester encoding basically solves this. So you can see our little bit stream. We have our bit stream 0, 1. I'm not going to read that all out, but basically we're sending bits onto a wire. Now we're at the physical layer. We're actually sending things on the wire at clock speed, essentially. So those little bars are the clock width, or what we're sending onto the wire. So in this case, we want to send to 0. So our Manchester encoding says, all right, well, we'll just go from a low to high transition. We'll transfer from very low voltage to high voltage. Okay, well then what if I want to send a 1? Well, we're already at high. So in this case, we want to say, all right, well, we'll go down to high. And now we're at 0, but ideally for our 1 transition, we don't want to say, okay, we're still at 0, but we said we want a high to low transition for a logical 1. So we'll shoot back up to high, and then we'll go down. Now, when this bit stream ends, where will we end? Will we end logical high or logical low? Well, in this case, idle will take whatever the last value is and just won't have any change in voltage. The change in voltage in the clock cycle tells us, oh, this was logical high, or oh, this was logical low. So in this case, when we're here, and this is the end of the bit stream, well, we'll just stay 1, 1, 1, 1, 1, 1, 1. Manchester encoding will just stay low, 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 low. Because now we're not sending anything else. Manchester encoding, we're done. So, the second time slice. This one, can you see my mouse?
Yeah, so on that one, like you see like how it's like 1 there, but then you have like a high to low transition in the encoding. Like I'm
Yeah,
confused
yeah.
about how I got.
How we got the high to low transition?
Yeah, like you see like how there's like a horizontal there's like there's no transition from like time slice 2 to time slice 3, right? It's still all 1, right? But why is there like the dips in
Yeah,
voltage?
so that's the whole idea of having the transition, because if we just said, all right, we're staying at logical high during this little time slice. I like the word time slice. It's a good way of thinking about it. But if we just stayed at 1, there's no transition, so that's just assume idle. Rather, we want to physically say, all right, something is happening during this time slice. So because we want a 1, we need to dip. We need to say, all right, 1 is Manchester encoding basically decided this rule. I don't know why, but if we're one to say, hey, logical 1, we want to send that, we want to dip. And that's the exact same reason why we want to send in the third time slice, oh, we still want to send 1. So we'll then jump up high before we enter the time slice, and then curve down. Does that make sense?
Oh, so it's kind of like if you want to keep the light on, you have to turn it off and on, basically, kind of, right? Instead of holding the switch.
Basically, because if we stay idle, if we stay at the same value, either on or off, the Manchester encoding basically says, oh, we're just idle. We're not doing anything. Does that make sense? Again, we're not going to talk about like how we actually send things on the wire. We're not going to get into the logical levels of voltage. That's kind of out of the scope. But you should be able to know what Manchester encoding is. I don't think in terms of like testing, maybe on homeworks you might have to do this, but in terms of testing, you should probably know how Manchester encoding handles like the binary encoding into actual physical wires, but you won't have to physically do that. Just know that Manchester encoding is how we handle, oh, how do we actually communicate what logical values are on physical layer? So that's it for physical layer. We'll talk a little bit more about the hardware of routing. This kind of gets into the network layer a little bit, or network to physical layer a little bit, so stop me if anything sounds a little bit weird. But we'll basically build up to the network layer. So we have a bunch of physical wires. We have a bunch of physical wires that are connecting a bunch of computers. So, well, if we have wires, I mentioned that, well, sometimes our copper wire can't always send out, like it can't send over long distances. So what happens if we lose all of our data, if we lose all of our electrical signals? Well, we introduce this repeater. Basically, repeater will take in the value no matter how low or high it is, and we'll just keep sending it. We'll introduce another jolt, and that will travel a little bit before it starts losing energy. That gets into physical and like probably physics, and that's disgusting, But we have a repeater and we have a bunch of wires. So how do we actually connect all these computers? Well, now we introduce the hub. Well, boom, now we have a logical bus. We have the Ethernet bus that we were talking about. And now we can say, all right, all these hosts that are connected on a physical wire, they're all in the same collision domain. This whole idea of, all right, can I send on the wire? Because now, if one of them is trying to send to any of these other people, well, they're basically sharing a logical hub. And the logical hub is responsible for, oh, this MAC address is trying to go here. This MAC address is trying to go here. So we have basically a little tiny mini hub. We can also have a hub of hubs. And all the hubs also act as repeaters. They also send out the data. They'll take it in, send it out fresh. So we have hubs, we have hub of hubs, but these are all on the same collision. So if one of these, like one of the hubs from this one of the computers from this hub wanted to talk to this, but another hub, vice versa, still we're in this collision domain. So either we have to manage the token versus all these hubs, or we need to more accurately split up. I have a private question basically saying, so is the hub like a pit stop station? That is a hard thing to say for me. If I were to send a packet or data. Yeah, exactly. It's a pit stop that says, all right, where exactly are you going? Frame of data, where are you going? Let me get you some more gas, the gas being like electricity. We're repeating that data, and then we're sending it off. So ideally, we don't want to have all of our internet basically being on a single collision domain. Because imagine if all of the internet was trying to talk to everybody at once, that would be chaotic. We don't want that. So instead, we're going to introduce bridges. Bridges connect bridges, the exact definition is they connect two specific hubs together, whereas switches can connect two or more. So I'll use switches in this case, like interchangeably. Basically, the book goes into more detail, but yeah, switches are essentially how we connect two different collision domains. Because now 1 and 2 can talk to each other, and 3 and 4 can talk to each other at the same time. Because now they're in different collision domains. They're in different wires entirely. But what happens if 1 wants to talk to 4? Or if 3 wants to talk to 2? Well, now we're bridging the two collision domains. And I'm fairly certain the bridge could handle intercommunication, but I'm not entirely sure. I'm trying to think. Yeah, Jonathan Ferris, could you double check that for me?
I'm not very
Yeah,
sure about that, but let me have a quick look on the text.
Yes, please. Thank you. Yeah, so I have a private question talking about the collision domain. So when we were talking about like Ethernet or basically sending things on the wire, and oh, what happens if multiple computers are trying to send at the exact same time? Well, that broadcast domain also conveniently the collision domain because anybody that's trying to broadcast in that on that wire can collide with everybody else that is also trying to broadcast. So is collision domain the area where collision is susceptible? Exactly. So 1 and 2 are susceptible to collision with themselves, and 3 and 4 are as well, but they're separate, so they can send on the wire. 1 and 4, if we were to like bridge that, I'm trying to think. I'm not sure if 1 and 4 and 2 and 3 could handle that at the exact same time. Um, there wouldn't be a collision between 1 and 4 unless 1 and 4 or 1 was trying to talk to 4 at the same time that 3 was trying to talk to 4. And I think in that case the bridge would have to queue up the frames of data in order to send that when the like connection with the hub wasn't a collision. Where the bridge basically says, one, you're directly connected to this hub when you want to be. Does that make sense? There are a lot of private messages, so I'm trying to like say them out loud, but how am I doing so far?
You're doing fine, but like in the case with the bridge, is it one whole collision domain? Because you just said like, oh, 1 and 4 could talk, and then 3 and 4 talk, and there could be a collision there. So is it one big domain? Like both those like hubs could be like one big collision domain?
Yeah, I think specifically the bridge is going to be responsible for getting the frames of data if 1 wanted to talk to 4. The bridge is going to basically act as a miniature node that talks to the hub. So only when one wants to talk to 4 will that like frame of data be in the collision domain. I am unsure if the bridge or the switch queues up packets. I'm fairly certain it will
Yeah, the
say,
bridge queues up packets.
yeah, it queues up packets so that whether that hub is a token ring hub or whether or not it's an Ethernet and will do the collision detection, we'll be able to send out those packets or the frames, sorry.
Oh, okay. So I see the separation, what you're talking about, and susceptibility to collision.
Hmm. Because then the bridge acts as its own node that is acting like on behalf of one, if that makes sense.
Makes sense. So
Okay, sweet. And then talking about switches, ideally we want to say, all right, this is still within a local area network. So how do we actually get away? What if I want to talk to Google? What if I want to watch YouTube or Netflix? Well, then sorry, virtual lands. I'll skip over this real quick. But basically, if I want to talk to anybody in my network, I just use my network interface card and I use my MAC address. But the moment I want to talk to, I want to talk to somebody else. I want to talk to Google. I want to get that information. I want to look up stuff for my project. I want to find a book online, or I want to find online shopping. Anything else that's outside our network needs a router. And every single router will hold its own information about IP, about the internet protocol, and we'll be able to say, all right, these frames of data, well, we'll packet it up into a nice little IPv4 or IPv6, and it'll have its own nice little payload, and we'll send it on its way. And virtual LANs, basically, what happens if we have a physical domain, like a physical broadcast domain of 1, 2, 3, 4? We don't want it to be like that. What if we want only 1 and 5 to act like they're in a physical domain, like a collision space? Well, we can basically make it so that the switches connecting 1 and 2 or 1 and 5 act like this. And I think that there needs to be a lot more beefy connections between the switches. I'm not sure about how it actually manages that, but I don't think we care too much. We more so care that you understand that we can virtualize our local area networks. We can virtualize the domain space, the broadcast space, if we so choose. And then we have the routers, like I said, that talk, and we'll talk more about how routers actually work and actually manage. Oh, how do we go from one router to another? And I think that's it. So, any questions? We talked about a lot. We talked about the physical layer. Really only need to know Manchester encoding. We talked about the link layer. Really only need to know Ethernet, the 2 types of collision detection and avoidance, what token ring does. And then we talked about some of the things about actually connecting all the physical layers together and how we actually got up to all of like the IP, how we get to network. We'll talk about networking later, so don't stress too much. That's all in my section. And with that brief little recap, I think that's it. If we have questions, we'll take them now. But yeah, thank y'all. This was fun. I enjoyed being a little guest. Ferris, thank you for having us. Yeah, we'll take some more questions and yeah, have a good night if you don't have any other questions.
For project 5, do we need to know about network layer and link layer, or if we know about stop and wait protocols and pipeline thing and other thing in transport layer, that should be enough?
Yeah, basically for project 5, you should look at like the network.c and network.h functions, and we gave you like the prototypes and like what they actually take in, but that's all abstracted for you. Your whole job will be you might need to use the network layer in order to like send acknowledgments, but you won't need to know how we actually are sending them, you know? Does that make sense?
Okay, yeah, that makes sense.
wait, Jackson, speaking of that, wait, so just
Yeah.
to make sure I'm extremely clear about this, so we're mainly doing the transport part. We're doing the actual like sending and sending the acts, but like everything else like below is like all like in the API of some sort, right? For Project
Yeah,
5.
exactly. You're basically the transport layer. You're taking an application data and you're sending it on the network, and you're receiving things from the network and you're sending it to the application layer. Or
Oh, so oh, okay. So we're like the ones that are like caring about like the UDP and all that. We care about that.
exactly.
Like,
Exactly. And that's why we care about the ACK versus NAC thing. It's very, very
I
close to
think.
TCP. It's stop and wait TCP, basically.
Oh, okay. So we're facilitating the we're facilitating stop and wait so that when we send messages and all that, sending the ACK and all that, like I feel like you said like was abstracted in the below layers, right? Because that's like sending a frame, right?
It's more like sending like the IPv4 packet, like an actual internet protocol packet. The frames get down way, way, way later, but that gets more in hardware that we don't care about.
Oh, oh, okay, okay. Now I see the difference. Okay, so now I see
Yeah,
what we're Project 5. I just
I
want to clarify.
probably should have mentioned that both the link layer and physical layer are both physical versus the network is still within like it's still within kind of software, and it's the bridge between software into physical. I probably should have mentioned that earlier, but it's in the recording, so thank God.
So we're not about talking about the hubs and like how the Ethernet wires
Oh,
connect
no,
and
no, no,
everything.
no, 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 no. Yeah, yeah, yeah.
Not
Your computer
that,
will
right?
handle that for you.
Oh, so that's what that Python command does? Because I was having questions about that Python command. So is
Oh,
it
which
kind of
one?
like doing that? There was that Python script that you put, like saying like, oh, run this Python script to connect to let's say like
Mhm.
3360 for SQL, right?
Yeah,
Is that so? If I run that script, like there's probably some function or library in Python's backend that's doing the actual like NIC stuff and the Ethernet and all that like hub stuff.
yeah. So it's called the socket library. We'll talk about that probably a little bit later, probably next recitation. But the socket library is this whole abstraction of, well, we're not going to worry about the physical layer because that's, well, wire stuff and we hate wire stuff. We're not going to worry about link layer because also physical stuff. And we're not going to worry about the IP. We're only going to worry about the transport layer. And that's what the socket basically abstracts all of that. And we just worry about the transport and sending things over the transport layer.
Oh, so basically we're really communicating with the socket, and in the socket's internal code, it's communicating with the 3 layers below.
Exactly. And the socket library will handle all of like the operating system will take all the socket information and be like, oh, where do I actually need to send this? And then once it's out of your computer, it's out of the hands and into the network.
Oh, oh, okay. So that's interesting because I always was thinking about like how does the internet really work, but I think today, like I think it's one step closer to that. I always
Yeah,
wondered like just of course, like how does the internet really work? And I always was thinking the internet's probably some wire, right? Through some fiber optic cable underwater or something.
there
And
are. Yeah, especially if I want to talk to my friends in Europe. I don't have any friends in Europe, but if I did, if I had like a pen pal and I wanted to do email, yeah, we would need a physical wire, and we probably couldn't send my email over wireless. Unfortunately, not yet.
oh, okay. Yeah, but thank you. I like seeing the energy though.
Yeah, I'm glad. Okay, perfect. Yeah. So, any other questions? We got me, Karthik, Natasha, Ray, Michael. How you doing? How's your night? I'm eventually gonna bounce to eat because I'm hungry, but yeah, we can stay a little bit longer.
Can you explain the envelope OS call again for the cons of user level threads?
Oh
Yeah.
yeah, I'll scroll back at Ferris if you want to talk
Oh
about
yeah,
that.
please.
Oh, did you say user or kernel?
That is user, I believe.
Okay, if you
Find
said
envelope.
yes, where would that be? Here?
Okay, not that. Yep, this one. Okay, so um, so yeah, in user level threads, there is a possibility that when a thread wants to send a blocking call, that thread will end up blocking the whole process. So we fix this by enveloping that thread call, and instead of say for example, the function name that we're trying to call is block. So instead of calling block, whenever a thread in a process wants to call block, we instead envelope that block function inside of a new function that we create. So say for example, thread underscore block. So whenever a block is called, it will go into thread underscore block, and thread underscore block will instead go through the thread library to ask what it should do right now. Okay, a thread is wanting to block. What should I do now? So it will go through that thread library. So that blocking call will never reach the OS, but instead it will reach one level inside the thread library first before going to that OS. But again, don't worry about this much. We will not test you on these types of fixes, but we do expect you to like understand why they work.
Okay. Yeah, that makes sense.
Cool. Jackson, you're
Oh,
muted
Jackson.
just in case you don't know.
Oh, I'm muted?
Yeah.
Oh, I was going to a long spiel. I was talking about how, wonderful TAs Ferris and Jonathan are, blah, blah, blah. Yeah. No, I was talking about how if there's any other questions, how we doing, anything
Mhm.
else we can help with. But that comment about y'all being good TAs does stand. I think for, being a guest appearance, we did pretty well together. So, good job, guys.
Don't worry, you both did an extremely marvelous job. Thank you so much.
Wow. Now you're just buttering me up. That's rude.
Okay, Natasha, Ray, do you have any questions? We can stay here longer if you want. I am going to stop recording right now.